We have two authors here. Brandon Forbes. Brandon is a hydrologist with the Arizona Water Science Center in Tucson. He's part of a team of scientists pursuing innovative data collection techniques to better inform hydraulic models and improve stream gauge data. And Jeff Debenedetto. I'm sorry, Jeff. I know I butchered that one. But anyway, Jeff is with USGS in Flagstaff, Arizona. He now works with a small team of talented hydrologists at the USGS, developing and implementing tools to improve data collection and analysis with the goals of improving daily operations, as well as providing timely information to stakeholders and cooperators for monitoring and decision making. You guys ready to go?
We're ready. Thanks, Judd.
Take it away.
All right. Thanks for the introduction. And today we're going to talk about some really exciting work that we've been able to complete with support from the Department of Interior's Inland Oil Spill Preparedness Program. This is going to be work that focuses on using drones to measure surface velocities over river reaches. We're building upon some work that's being done at many of the stream gauges that Peter showed you guys yesterday, where people are measuring surface velocity at the gauge location with a drone. In this case, we've come up with a workflow and a presentation and publishing technique to try to do that over an entire river reach. We're very excited to bring this work to this conference, and this is the first time we've actually presented results from the past year's work. So we're excited to talk about it today. Go over the outline briefly. We'll talk first about how we've arrived here and why we find unmanned aircraft systems to be so valuable in this arena. We'll then go into what we need to collect at the site to calculate reach scale surface velocity data. We'll talk about some publication techniques and how it can be useful during the response. And then we'll talk about next step, as this is just phase one of the project. Disaster response is an integral part of USGS's mission, and our team has been fortunate to be a part of many disaster responses over the last 10 years. Most of those responses involve flooding response, whether it's riverine or hurricane storm surge response. But we've also had the opportunity to study Kilauea Volcano as it erupted. And we've learned a lot of really important lessons during this work. And most importantly, it's collecting the right data at the right time and making it available when it's actually useful. And we learned this especially in Kilauea Volcano, is that we're collecting data that can be useful in a very limited software, for example, that maybe many people don't have access to. So being able to parse down data and deliver it in a timely manner, and even resample data if necessary to make it available to the masses during the response is really important situation. And on the bottom right, there's just an example of our flood response viewer where you can see real-time measurements of flood inundation occurring after a hurricane in southeastern Texas. So surface velocity. We've been measuring surface velocity for over 130 years at USGS, and you can see on the left there, that's a picture of somebody in the bottom of the Grand Canyon in the 1930s measuring surface velocity. In the center, that's a modern picture of Lee's Ferry, which is just above the Grand Canyon, where we're using boats and cableways and instrumentation to measure surface velocity. And you can see on the right there, that's one of those point velocity measures using drones where we're measuring movement between frames, which we're going to talk about today. But that was the first time we really employed surface velocity measurements in a disaster response environment. And a caveat, on days where the eruption was at its maximum, we were measuring between 45 and 50 miles per hour of lava movement coming out of that fissure. So why are UAS important in disaster response environment? I'll start off with being a Department of Interior pilot, we have some unique rules. We're actually able to fly up to 1,200 feet above ground surface, even if a TFR is not in place, and we can go out 2 nautical miles and beyond line of sight. So we have some advantages to our data collection that makes these tools really, really valuable to us during disaster. As you're going to see here, we can get really high resolution data, and in this case, we're collecting imagery and video, and it keeps our people safe And while putting equipment that's very inexpensive in harm's way, the two drones that we're going to talk about today cost less than $1,000 and can be deployed really quickly and safely. It's a really big value to our personnel. And for this test, we had to pick a site that we could operate safely during COVID restrictions. And we needed to pick a site where we could get both a flood condition and a low flow condition. And so the experiment we're going to talk about today has taken place in Moab, Utah over last summer.
All right, can you hear me?
We hear you, Jeff.
Now the slides won't advance. There we go. Okay, thank you, Brandon. So I'm going to talk about the data we collected and how we did it and what we're planning on doing with it. So when we got on scene here, the first thing we wanted to do is create an ortho image. And to do that, first thing we're doing is going out on the riverbanks and laying control markers that we're then surveying in with RTK differential GPS so that all of our data we can plot in that 2 to 3 centimeter range of uncertainty and get on a map in the appropriate location. And then we're pre-programming a mapping capable drone to go out and fly for us so it has good geometry using a decent camera and collecting a bunch of stills. And then we're taking all those stills and GPS data and processing that through some photogrammetry software to come up with our model. A byproduct of that model is point cloud, a digital surface model, as well as our ortho imagery. And you can see in when we were in this location on the Colorado River outside of Moab, this is from our October collection. We did about 2 miles of the river. It took us about 30 to 40 minutes to collect that data. And as we zoom in here, you can see it gives a good profile of the river in that current condition, you know, in a pre-spill environment. You can see what you had first, and post-spill, you can see what has happened. And because of the UAS and our flight restrictions and altitudes, we're getting generally 2 to 3 centimeter pixels. So real high resolution data, providing great information. Then after we've collected the data necessary for our ortho imagery, we're going out and collecting a bunch of discrete videos of the river from a more cinematography focused drone. And we collect anywhere from 30 seconds to 2 minutes of video looking straight nadir at the water, framed up with the banks on either side. And at 4K video at 30 frames per second. And with about 30 seconds, we can well profile what's happening in the river and measure velocity. If the river has things like unstable eddies or boils, upwelling going on, we would collect over a longer duration of time so that we can then average out some of those transient effects that we see in the river. But the reality is, with about 2 seconds of data, we can actually physically measure what's happening in the river. So we'd go out and hand fly, and take our video, framing up the banks here. In the lower left corner of the imagery, you can actually see one of our white and blue checkerboards down over here that we're using to survey in with control. We would collect our 30-second video, and then we'd move up or downstream, whichever direction we're starting from, and then keeping a segment of the stream from the last video in the next video. That way we have overlapping data and we can generate a continuous data set. Once we have those videos all collected for the area of interest, we then extract stills from the video. So we're getting 30 frames per second, 30 seconds of video. We have 900 stills to work with. We process those stills through a video stabilization software that takes out any motion drift from the drone, so we're not getting any sort of bias from the air as the drone's hovering there. And then we're going back to that ortho image we created in the beginning. We're taking those 900 stills from each video and placing them on the ortho, giving them reference. And so not only are they placed in space, but they have appropriate scale. This is very important for our process because that eliminates any sort of lens distortion from the camera, as well as any effects of a rolling shutter video process, and makes it so that no matter where you're looking in the video, those data that you're extracting are not influenced by any sort of light disturbance or bend. And then we run those now corrected stills through large-scale particle image velocimetry software. And that software is measuring the displacement of particles on the surface of water between frames. And so 900 frames for 30 seconds, we're getting 899 discrete measure points of what's happening in that video of the river at that time. And so going back to our video we showed earlier, we have our little video and you can see velocity vectors plotted on the surface, and in areas where the flow is real dominant, the vectors kind of hold still and go the direction of the flow, and in areas of circulating flow or somewhat unstable flow, you can see there's a little bit of noise and dance. And over the course of 900 frames, the data gets averaged very well and represents what's happening in the channel. So for the study we did, we were there, and this is Colorado River, just east of Moab. We were there in June, and it was flowing at 12,800 CFS, and we went back in October when it was flowing at 2,400. As you can see, with any data collection, you go do it once and then you think, I want more. So when we went back in October, we flew 2 miles of river as opposed to about 1 mile of river on the first collection there. So for this metric here, we're looking at magnitude, we're looking at the velocity of the river, and the scales are fixed. So the scale ramp is fixed to the data of the higher flow value, so you can see as compared to the lower flow, there's a dramatic reduction, obviously, in velocity of the river. So we've zoomed in here to an area, and you can pick out from these data what's happening in the river, how fast it's flowing, but also this is useful in that, say, if you had an event or a spill and you want to know if you could access the river or what's happening in certain areas, you might be able to determine that you can access in certain areas, or you can get in a boat in an area, use particular equipment based on what's actually physically happening in the river. As a byproduct of our data processing, we're getting second and third order equations here. So we're getting shear force as one. And here's a plot of shear. The scales aren't fixed on these ones. Otherwise, you wouldn't be able to see much of anything in the lower flow condition. But if you had a flow event, a spill event, and you wanted to look at frictional forces in the river, maybe look at how your oil might change phases, become a foam, how that's going to propagate through the channel, how things will change. And if you had metrics on, what velocities would require that, what rates of change would require composition change of your oil, you could actually look at the data and make some assumptions and start getting at what's happening to the fate of the oil. We're calculating divergence, so the vertical movement of flow. If you were concerned about your surface slick interacting with bed materials, you could look at areas that are real brilliantly blue, moving vertically down, interacting with bed material, and potentially falling out of the water column, where you might need to sample for potentially dredging in your river channel. And then lastly, curl or vorticity, looking at rotation within the channel. And so if you wanted to isolate an eddy or somewhere where you had a high amount of rotation or somewhat stable rotation, and you could go out and start doing booming or skimming operations, you could look at the rates of rotation and if that area was appropriate for what you're looking to do there in the river. And then where we're going next, and kind of the big vision for us, is we want to make the work we're doing, these data we're collecting, useful. We want it useful in that response environment. And so we're working with Tableau servers and web-based interfaces where we can rapidly get these data up on Tableau, and it can be accessed through a web page. And so in the incident command, these two panes on the left and center are from the computer-based application where you can get the data. You can actually zoom in or isolate certain areas of interest if that's important to you. And the great thing is you can actually download a CSV file of all the data that's collected, whether it's the whole data set or an area of interest, and then work with that data however you want. And so you can make decisions and actually have the data on hand. Another great part of Tableau is it's fully mobile enabled. So if you have location services turned on your phone, you can be stream side as a SCAT team member, a first responder, or someone that's tasked with going to a specific location and be able to identify if you're in the right spot. Does it match what you saw earlier? Are the flows appropriate? And make decisions on the fly and provide for accurate data, accurate collection, as well as the safety of the staff. Where we kind of see this going, the way working for incident command is potentially areas of critical infrastructure, maybe pipelines across highways, places of potential spills or interest, data collection in advance. And so data collection over different ranges of flow. That way the river is profiled in advance. And if something did happen, decisions could be made rapidly on the fly, find a discharge that then matches the conditions you're seeing. You could use the 10-day riverine forecast to look at what's going to be happening a week from now and if those conditions match, and start making decisions right away. And then also look for like focused efforts where you could deploy someone to go out and then collect the data rapidly. Or in a response situation, if there is no data available, techniques can be adapted to collect data quickly and potentially have, depending on the extent and reach of interest, you could collect and look at areas and turn those data around within hours to a day or two, depending on how big of an area you wanted to look at or the repeat sampling of a certain area. So that is it. As Brandon mentioned, this was funded through the Inland Oil Spill Preparedness Program. We have excellent cooperators within the USGS who've supported this and helped guide our vision here. And what we would really like to know is we want to make this available and useful in a response environment. And so if you all have ways that we can tweak what we're doing or things that are of particular interest or ways that you see that this could be more useful, we would absolutely love to hear from any of you on how we can do this and make it useful for you. So the web address at the bottom, if you email that'll go out to our entire team, and we'd be happy to know what you think and how we can do this.
Okay, thank you, Jeff and Brandon. Just off the top of my head, or my first gut reaction is the true value of this is in the pre-planning. We're in California, we're going through an exercise now of creating these geographic response plans for all the major rivers and streams within the state of California. And like I mentioned earlier or yesterday, we don't really have a good tool for measuring flow at different times of the year. As far as response goes, well, by the time you got here, the oil is probably already downstream and stranding along the banks. But again, with the current patterns, we would know where to look for that stranded oil. So this is a great tool.
Absolutely. What we're thinking too is if you had the data in advance, you could say, hey, I want to go to this eddy. I think we could put out some boom material and potentially skim some oil off the surface. Can you go out to that particular spot and collect data? And then we can size our anchors. We can look at our booming patterns, our apron depths, and then actually be able to evaluate how well that's working. And so, yeah, we kind of that combination of being able to finally pinpoint collection and ensure you're getting what you want, or inform SCAT, as well as collection in advance that can help make decisions when the decisions need to be made.
Yeah, we would certainly know where to send our reconnaissance drones.
Right. That'd be great.
Okay,